Well, apparently, I forgot to hit the record button when I started class this morning. So I'm going to record a video. Should be a little quicker, so I can put it up for there were about 5 or 6 people that didn't make it to class this morning, and we were talking about physical optics on last Friday, where we showed Maxwell's equations predicted that electromagnetic waves, light is a special case of that. Um, well, they're waves. Okay, light is a wave. And this is our model, electric fields oscillating up and down as the wave moves, in this case, to the right, being accompanied in all cases by a magnetic field that's perpendicular, such that if you cross the electric field with the magnetic field, your your thumb will always point in the direction of motion, a wave. Unfortunately, this semester we don't have time to talk about polarization. Okay. It is a wave phenomena. It talks to the orientation of the electric field. And one of the things we find is because light is a wave, there's ways to filter out particular orientations of electric fields. Orientation of electric field is kind of a synonym for the polarization of the wave. And as I said, we're able to block those out. Unfortunately, we don't have time with the loss of a couple days this semester to talk about polarization, but it's an important wave phenomenon. We will be spending a little bit of time today talking about interference and diffraction. And diffraction, in a general sense, is just the ability of a wave, be it electromagnetic or mechanical, to bend around a barrier of some sort into a shadow region. If you've ever seen water waves and a jetty protecting a harbor, okay, you certainly create what we people in the Navy call a lee area here, where the waves coming in from out in the ocean don't seem to be having any effect because we put a barrier in place. But the pattern is such that it's not a perfect shadow right here. There is some bending of the waves around the corner and impinging into the shadow region that we hope to have happen. And sometimes we get two barriers and we create an opening, maybe some size A right here, and you can see bending around both sides in that case. And when you make the opening size, this value of A, much smaller, these almost become little spherical wavelets. Okay. And this diffraction that we observed by Grimaldi in the 17th century, it occurs best when the wavelength and the size of this opening are about the same. Now, I'm showing these wave fronts right here, just so we're clear what I'm drawing. We're thinking about something like that. And so I've connected peaks here. And so the separation between these two is about one wavelength. And you can see that's about the opening of this aperture right here. So when the wavelength and the aperture are about the same, we see diffraction fairly well. Huygens was the guy who first came up with an explanation of why we get this bending. Why don't we see shadows? And I suspect the most the best demonstration of the shadows we might see is if you went over to the theater department and you saw one of those big spotlights they had, and you shined the spotlight, say, on something, an opening maybe the size of a door, a meter or so. What you would see beyond the door is a shadow. And yet, when the wavelength of the light, which it's nanometers, hundreds of nanometers, red light is about 630 nanometers. Take a micron, which is a thousandth of a millimeter, and chop that up into a couple tenths. That's how big the wavelength of light is. Well, obviously, the door is many orders of magnitude bigger than that. So you see shadows in that case, and they're pretty sharp edged. But when the openings are close to the wavelength of light, you see this bending. Well, the way it was justified originally was by Christian Huygens. He said, on these wave fronts, you create these little sources, which he called wavelets, and they spread out in a spherical fashion, both into and out of the page, as well as in the two dimensions of the plane I'm drawing in here. And that's what allows the waves to continue along. And then, of course, when you get to a barrier right here, some kind of masking off, well, the wavelength that's at the wavelet that's at the very edge, it continues to spread out spherically around the edge. And that's how this works. Now, there's a lot that's unsatisfying about Huygens' construction here. It is something that you can construct really neatly with a compass and it's all well and good, but there are some questions not answered, like why does it work? And then, of course, the other one that I find most inconvenient is it says he said it spreads out as spherical wavelets in all directions. So how come these wavelets don't propagate backwards as well? Okay, how come they don't propagate that way? We always seem to see them going in the direction away from the source. How come the wavelets don't cause propagation back towards the source? And so there's some issues with Huygens construction, but it does explain to us why light bends around some kind of barrier near its edge. Now, we're going to refine Huygens construction because we're going to point out these wavelets. They have to obey superposition. Superposition is a fancy word for adding up of waves. And we notice that if two waves are oriented like this, and these are ends of a continuum, there is stuff in the middle between this. Okay, we could be fully destructive interference where it adds as it does on the right here, and fully constructive like it does on the left. We say these are in phase where the crests line up with the crest, the zero crossings line up, the valleys line up, and then we just get an adding of the amplitude of the two waves. When that occurs perfectly, we refer to it as constructive interference. When we're 180 degrees out of phase, so a peak lines up with a valley, the zero crossings still line up, but a valley lines up with a peak, those add as complete destructive interference. Again, there's things in the middle in between those. I could have not 180 degrees out of phase, but only maybe 90 degrees out of phase. So a quarter of a wavelength out would be something in between. It wouldn't be perfectly bright, we'll be call it, or it wouldn't be perfectly dark, but there'll be something that's just kind of a smeared in between amplitude for the brightness. Okay, and that's superposition. That is the basis of everything we're going to talk about today. Particles don't do that, do they? Okay, well, we'll see. Particles don't do that. Waves do this. And so this is a wave phenomenon. And so here's the question, I guess. Young had an experiment. He brought in sunlight, and I'll draw some wavelet, some of these wave fronts that have wavelets along them. Okay, and so this is about one wavelength right here. And you notice that's about the separation here, which we're going to call D, between the two openings in this, I don't know, it could have been a piece of cardboard or something, piece of paper he'd set up, and he cut two openings in it. And of course, the question is, what are you going to see over on the side here? Are you going to see two bright lights with a shadow region on either side of it, like you would find if you took a theater light and shined it on an open door frame? Are you going to see just two bright spots in the shadow, or are you going to see something else? And of course, the answer is something else. And here's why. Okay, at the very center right here, halfway in between these two openings, I'm hoping it's fairly self-evident that these light sources will have electromagnetic radiation oscillating back and forth, traveling exactly the same distance. And so I expect constructive interference to occur at that symmetric halfway point, and I expect a bright spot right there. And I think there should be another bright spot if, say, for example, the bottom source travels an extra distance, and notice what that extra distance is. It's exactly one wavelength right here, right? If it's exactly one wavelength, well, when the light arrives at the screen over here, it's still going to be in phase. It's still going to exhibit constructive interference. And so I expect a bright spot right there as well. And there's no reason to think that there wouldn't be a symmetric location down here, which would also give me a bright spot. So 3 bright spots, I suppose, and nothing stops this. And I can go to an even bigger angle. Okay, and instead of just having one extra wiggle, one extra wavelength right there, I might have 2 extra wiggles in that same distance. And so if the difference between that path and this path right here is 2 wavelengths, oh, that's terrible, is 2 wavelengths out there, well, that would be a bright spot also, wouldn't it? Sorry about all this. I must have hit something with my mouse. Okay, and so there might be another bright spot down here. And that's the pattern we see. We don't get a shadow with 2 bright bars like you might expect from a bigger opening. We get bright spots from constructive interference at particular angles on the other hand, in between, maybe right in there, what happens? Well, in that case, if you look, the bottom source might have to travel only a half a wavelength extra distance compared to the top. A half an extra wavelength difference would be destructive interference, and I expect a dark spot right here. And it shouldn't be too much of a surprise that there's a dark spot in between those two bright spots and another one right there. And even back over here where I've got this lousy line, I get dark spots. So the pattern you should see is start into the center, a bright spot, a dark spot, a bright spot, a dark spot, a bright spot, and exactly the same thing if I go in the other direction from the zero angle, which we call sometimes the central bright spot. Okay, a little bit on the math of this, okay, and it all comes down to the distance between the light that's traveling from the two openings, which we refer to as S1 and S2, which we said would be separated by some distance d. And so I'm going to blow up this guy right here. There's my two openings. There's that distance d right there. And coming out of these openings are two rays, which are perhaps heading to a bright spot right there, okay, at some angle. And there's the angle. And I think if that's the angle, well, that's also the angle right there. I think right here is 90 minus the angle, and also would be 90 minus the angle right there. And so right here, which I guess if I dropped a perpendicular right here, would be this same angle right here would be theta. And it's right there by S2, okay? Hopefully I've kind of made a little proof. Theta, 90 minus theta back to theta right there. If I drop the perpendicular, which is what that line is, okay, that angle and that angle, the angle to where the bright spot would be is the same as this angle right here. And we said the constructive interference is predicated on this extra distance right here being a full wavelength. If I have a bright spot, if I have constructive interference. Well, hopefully you can see I've got a little right triangle right here. The separation between the openings is the hypotenuse. This side right over here, this little extra distance, is associated with the sine because it's opposite the angle. So d times the sine of theta is that little extra distance. If it is exactly a wavelength or two wavelengths or three wavelengths, an integer multiple of wavelengths, m can be any integer, 0, 1, 2, 3, minus 1, minus 2, minus 3, okay, I should expect to get a bright spot, a bright spot, a bright spot, a bright spot, and a bright spot. All right? Now, if this distance L here is significantly bigger than this distance D right here, we say we're in the far field, okay? And in the far field, very often these angles right here, that angle theta is small. If the angle is small, then theta is approximately equal to sine of theta. Check it on your calculator sometime if you don't believe me. Put in, and it has to be angle in radians now, okay? But for radian angles less than about 10 degrees, whatever that corresponds to, you'll find that if you take the sine of that angle in radians and you look at the angle you started with, they're about the same. And the same is true for the tangent of that angle. So you can replace sine of theta here with just theta if the angle is sufficiently small, okay, well, like these seem to be. I just brought d to the other side of the equation, and so the angle is just m lambda over d. And then if you're ever trying to find out what this distance y is from the central maximum, I think theta would also be y over L. It's actually tangent of theta, but if we're saying these are all equal, then theta is equal to y over L. I can just solve for that distance by bringing the L over the other side of the equation. And on the worksheet for today, which is worksheet 36, I have you both calculating the angle, okay, and calculating the distance y for one of the angles. And so that's an important thing. Now, what about in between these bright spots, in between these maxima, in between these points of constructive interference that give us bright bands? What about right here? Well, right there, I think if that extra distance, d sine of theta, is a half of a wavelength, or 3/2 of a wavelength, or 5/2 of a wavelength, then we should get destructive interference. We should get minimum. We should get dark spots. The problem is, of course, indexing that. How do I come up with a pattern so that I get an odd multiple of 1/2 of a wavelength? Okay. And so what we do is people have used this thing right here where we say m once again can be 0, 1, 2, 3, 4, 5, any integer or a negative number, I guess. And that leaves this being 0 plus 1/2, that's 1/2. 1 plus 1/2, that's 3/2. 2 plus 1/2, that's 5/2, etc. And so you only get an odd integer multiple of 1/2 in the parentheses right here to multiply by wavelength. And you can then calculate the angle at which these dark spots, these minimum, occur. All right, hopefully pretty straightforward there. Here's what the pattern looks like. Okay, for the maximum, m times lambda is equal to d, the separation between the openings, times sine of theta. It's pretty easy to follow what m must be. There's m equals 0. Next one out is the first bright spot, then the second bright spot, then the third bright spot. I didn't quite line them up like I might have wanted to. I had to squish that thing together a little bit, but hopefully the location of these bright spots, the angular location, or if you need to, the distance, okay, y right here would be, that would be what I've called y before. Okay, hopefully that's fairly straightforward in terms of how I'm indexing. And it is sometimes conventional to call these over here negative. Yeah, I think you saw that in a preview. Yeah, I made these negative over here. Okay, not necessary. It just reminds you that it's on the other side. Symmetric angles, though. Okay, it should be the same angle for the 1 and the -1. Just one's over to the right, one's over to the left. That's all that matters. Now, but be careful on the dark spots, because on the dark spot, I got m plus 1/2 times the wavelength is equal to that extra distance. That gets me destructive interference. And as a consequence of how we've tried to set up an indexing so that I get 1/2, 3/2, 5/2, I've set this up. The first dark spot right here is called m equals 0. The second dark spot is called m equals 1. And so if you're looking at that, that would be m equals 0 right there, the first one. And that would be m equals 1. And so, as you might guess, when asked to find the second dark band, a lot of people put m equals 2 without drawing this picture to realize the second dark band is either m equals 1 or -1. Okay, so just pay attention to how the indexing is. You sort of have to learn this diagram goes with this equation. This part of the diagram goes with that equation. Okay, so that's what the pattern looks like. All right, it may be an interesting point to, just because we're all liberal arts type folks here, to make a broader point about Young's experiment. And I want to go back to the original, and let's get rid of the light rays here. And in the late 1800s, scientists had been able to isolate something that they called cathode rays, okay, just beams of electrons. They didn't know they were electrons at the time. That much of an atomic theory hadn't been developed yet in the late 1800s, but they were able to create these beams of something, okay, cathode rays. What if I put a beam of electrons all moving that way, and those things would hit those same two openings? Okay, interesting problem. And here's the results. Let's say you put back on that screen a photographic plate, and you can see every place I get a little bright spot right here. Those are all little dots where electrons hit the photographic plate. And so this experiment is allowed to go on for quite a bit of time. And you can see after a bit of time, there's kind of a random orientation. It just looks like maybe stars in the nighttime sky. And then you let it go a little longer. There's still some places where it's pretty thin in the number of electrons hitting the plate. But if you let it go for even longer amount of time, well, then hopefully you're seeing there's definitely a bright range right here, a bright range right here, and a bright range right here, bright bands that seem to be constructive interference. And then in between them are these regions of destructive interference. So apparently electrons periodically are able to behave like waves. And so, the chemists out there are probably going, no, 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 electrons are particles. I'm sure of it. At the same time, sometimes they interfere just like waves do. So sometimes things we think about as particles behave like waves. The bottom line, I guess, is nature doesn't necessarily subscribe to our labels, does it? Nature behaves like nature is going to behave. And we have to kind of adapt our thinking to um, broaden out to accept the possibility that things that we think about as particles at time exhibit wave-like properties like interference and diffraction. That's just the way it is. Okay, we don't rule nature, we try to figure it out. All right, I want to move on a little bit because we got to keep talking here about interference versus diffraction. They're both superposition phenomena, destructive and constructive interference. But it is conventional to call the superposition of multiple sources of waves, call that diffraction. And so um, I'm broadening out my definition of diffraction from Huygens construction and that original concept of just bending around. Anytime you get constructive and destructive interference from wavelets, they come from multiple sources, we refer to it as diffraction. Okay, and amplitudes here are superposition is the way they're added. Okay, we didn't necessarily say that in the original construction with Huygens, but now we've come to understand they constructively and destructively interfere these Huygens wavelets that we talked about earlier on. Okay, so that's Fresnel's correction to uh, Huygens principle. I do want to point out something called a diffraction grating here. It's pretty simple to make, I guess. It's one of the things that folks were able to do. You just take a piece of glass like a microscope slide, and you take a ruler and you etch lines on the glass pretty close together, much closer than I'm showing here. And if you ever taken a etching to a piece of glass, what you find is you make it opaque, right? The light doesn't go through where you've etched. And if there's spacing, the light will go through right there. That's the opening right there. And where you've scratched the glass and made it opaque, that's the line that I've drawn right here. And so openings are here. And if you had a laser beam or some light source shining on this diffraction grating, and I've shown 3 lines, in reality, there's hundreds of lines per millimeter. So think about how close together these lines are. What you find is you get a lot of sources of light that is going to interfere. And so while 2 slits will look like that, it turns out if you went to 3 slits, you'll get a slightly narrower, and then you'll get this little intermediate guy in the middle here. And if you go to 4 slits, you'll get a couple intermediate guys. And these principal maximum here, these guys get narrower and narrower. Okay. And if you have, like I said, hundreds of these things, because you've made hundreds of little lines on a piece of glass, they'll get very narrow. They show up as points of light, or maybe very, very thin lines of light. Okay. The good news, the equation is exactly the same as for the bright spots right here. The bad news is you don't have a destructive interference point because you've got a lot of destructive interference going on in those regions right there. So there is no point of destructive interference. So you can have m plus 1/2 quantity times wavelength is equal to d sine of theta. All you can do is predict where the bright spots are. The good news is those bright spots are exactly the same place as the bright spots were in the 2 slit interference pattern. Okay, so that's a diffraction grating, not much new. Over 2 slits, there's just a whole bunch more, and that's kind of about it. We talked about the far field before. We refer to that now. I've named it after a guy, Fraunhofer. Fresnel, he studied things that were a little bit closer in. And of course, he's the person who I said corrected Huygens construction. Okay, we're going to stay in the Fraunhofer region, the far field, for what I talk about next and what I've been talking about till now. Okay, so what if I had, instead of an opening, I had the inverse of an opening, a blockage. And the way people often do this is they'll take a microscope slide and put like a dot of paint and then illuminate the dot of paint with, say, a laser and look at the shape of a shadow is what you'd expect on a screen some distance away. And you do get the shadow. The interesting thing, though, is at the very center of the circular shadow you get from this you find a constructive interference point, because all the light that's hitting around the edges of the blockage, this solid disk here, they're constructively interfering right at the exact center. And so you actually get a bright spot right at the center. Who'd have predicted that? But it's there, and it's a very easy experiment to do. Okay, so now let's go back the other way now, not just blockages, but now we're talking about openings. And let's say I've got just a single opening, not two like in Young's experiment, but just one. But the width of the opening is some width A. Okay, well, straight on through, zero angle. I hope everybody would expect a bright spot. Okay, and so let's do the same thing we did with Young's experiment. Let's tilt the beam, okay, at some angle, such that the very top ray right here and the very bottom ray right there, they differ in travel to the screen, which is some distance away, by a full wavelength. Now, for Young's interference, when the two sources differed by a full wavelength, that was constructive interference, and that gave us bright spots. In this case, the end rays differ by a full wavelength. And yeah, it's true, they do constructively interfere, but look at every other ray. If you look at one halfway and this one down here, they travel a different distance by a half a wavelength. So this one interferes destructively with that one. And that must mean that this guy right here interferes destructively with that one. And this one right here interferes destructively with that one. So it seems like you can divide the opening, the aperture, into two segments, a top and a bottom. And every ray in the bottom interferes destructively with a ray at the top. And so I'd expect, if I allowed that angle right there to shine on a screen, I'd get a dark spot. And a bright spot right at the center, I'm getting a dark spot right here. And that one corresponds on my diagram to one of these two. It's the first dark spot either side of the central bright spot. Okay, let's continue this argument along a little bit. Now let's let the top ray differ from the bottom ray, not by one wavelength, but 1.5 wavelengths. Notice we did skip a half a wavelength, didn't we? It would be right about here, and there's nothing special going on there. But at 3/2 of a wavelength, okay, now I've essentially divided the aperture into thirds, okay? And if I've got 3/2, then it seems to me that every bit of light that's in that third interferes destructively with that third, but there's still a third of the opening that doesn't interfere destructively at all. And so I think that gives us this point right there. It's not a maximum like it was at 0 degrees, but it's not a full minimum either. And it's a predictable piece. Okay, keep going. Keep going. At 2 wavelengths of difference between the top and the bottom, this would be like dividing the opening into fourths. And if you think about it, any 2 adjacent ones, like this guy right here, interferes destructively with that guy. And this guy right here interferes destructively with that guy. 2 adjacent quarters here would destructively interfere with each other, the top 2 and the bottom 2. And so I would expect at 2 wavelengths of difference between the top and the bottom, I would expect destructive interference. I would expect a dark spot. And I think it's that dark spot or that dark spot, depending on which side of the central maximum you're at. Okay, so we've got a conclusion here. I don't have a way to find these bright spots right here, but I do have a pretty good prediction for the dark spots, because this top to bottom, okay, so that would be that extra distance right there is now not d sine of theta, but for exactly the same reason, that's a times the sine of theta. If that is an integer multiple of wavelengths, the integer we use in this equation is p. Why p? I got nothing. I don't know. It's just an integer, and it's 1, 2, or 3, not m like in the interference case. It's p, and p doesn't have a 0. It only starts at 1, 2, and 3. I can find the angle at which the dark spot occurs. You tell me which dark spot it is. Tell me what the wavelength and the width of the aperture is, and I can figure out what the angle is. I will say that in many cases, the small angle approximation applies here too. So in many cases, you can replace sine of theta with just the angle theta. You can see I brought the a to the other side of the equation. So an integer multiple of wavelengths divided by a is the angle theta. And if somebody says, well, how far in distance out to one of these dark spots, you can just solve for y, because the distance from the opening to where the screen is called L, and so y over L would be that angle theta. Okay, I do want to point one thing out about the small angle approximation. When we talked about diffraction gratings, notice I never mentioned using a small angle approximation. That wasn't an omission. It's because of the relative spacing in between the lines, which means in between the openings here in the diffraction grating, the relative spacing of those is such that the angle at which these occur is often a pretty big angle, 30, 40 degrees. And so it's inappropriate in that case to use the small angle approximation for diffraction gratings. You can pretty much count on it for interference patterns. You can count on it for single opening, single slit diffraction patterns. You can't account on a small angle approximation for diffraction gratings, okay? These angles right here are often small enough though that you can. I do want to just put the two things together, the interference pattern, and I've shown a diffraction pattern from a single source from one slit here is what I'll say, okay, looks like that. Interference pattern from two slits, remember, looks like this. And if you notice when I actually showed you a photograph of that interference pattern, as you got further from the zero angle, it kind of mushed away into a kind of just a darkness. And it wasn't out at 90 degrees. It was at a fairly small angle, maybe 5, 10 degrees, like it's shown on this diagram here. Here's why. Superimposed on this two-slit interference pattern, the Young's experiment interference pattern, is the fact that each of the openings in Young's experiment is of themselves a single slit and creates the top pattern. And so what you see is this mushing out at larger angles. You might get 1, 2, 3, 4, maybe a fifth bright spot, and then you get a dark spot out there from the single slit pattern, okay, being superimposed on top of this. And if you look, that's what we're seeing here, right? Okay, so we got bright, dark, bright, dark, bright, dark, and it keeps repeating. I don't know, maybe get 7 or 8, but then out here, that single slit pattern is what's being superimposed. There might be a little pattern out there where it gets a little brighter again before it completely goes away. And there may be a couple of those, each one getting less and less. But in this case, we're only seeing out to that first minimum right here, which happens when m times lambda is, actually we said p times lambda is equal to a times the sine of theta, okay? And so that's what we're seeing. All right, so we put it all together here. We've talked about interference. We've talked about interference gratings. Diffraction gratings is what we truthfully call them, but I think they behave more like interference gratings. And then of course, we talked about diffraction from barriers and the single opening, the single slit experiment, and that's what we have to do. Worksheet for today is worksheet 36. I think I have it due on Wednesday. And we'll stop sharing and stop the video here.